Welcome. Today in the third lecture of week 2, let us discuss about soil and how the soil health matters as far as climate change happens. So, in this context, as far as the soil and soil health and climate change, let us discuss about these concepts. So, we will have first an introduction to soil health, then we will try to understand what are the different indicators for understanding the soil health and various responses of soil as far as the climate variables are concerned. And we will also discuss about the various land use systems and how it matters as far as the soil health and climate change is concerned. And finally, a few points we will also take into our discussion as far as the climate smart soil management is concerned. So, this in turn will give us some ways or some advices or some guidance how to manage the soil in the context of this warming world or the climate change. So, to understand this, let us discuss about various components of the soil health. So, we put it in three categories: primarily physical, chemical and biological. These are the three broad divisions of the components as far as the soil health understanding is concerned. And then we also take two together, like the biological health and physical health, that talks about biophysical health, the physical and chemical health that talks about physiochemical health, and then the biological and the chemical health discusses on the biochemical health. So, two taking together, and in totality taking all three together also we discuss in terms of biophysiochemical components. So, friends, as far as the physical health is concerned, the various broad parameters what we understand here are texture. First is texture. It is smooth, it is coarse, or what kind of or what is the texture of the soil. Then the structure, how the structure of the soil is, and the porous and the pore size distribution. Porosity is very important as far as the movement of the exchange of the water and air is concerned. Then we will also discuss, we also understand the physical health in terms of the water retention and transmission, because this is important as far as the soil means the plant growth is concerned, or the plant system is concerned. So, water retention and transmission is another important parameter under the physical health. And then we also need to understand the aeration, how good it is aerated, and the thermal regime. So, we plow the soil to facilitate the many of these things in terms of a smooth texture and porosity and pore size to increase, so that it will facilitate aeration and the transmission also. So, and also the thermal regime, particularly the temperature, how hot it is. So, we need a varied range of temperature to sustain the plant system, the biota or the microbial system. So, the thermal regime, understanding the thermal regime as far as the physical soil health is concerned is important. Now, let us move on to the chemical health. As far as the chemical health is concerned, we need to understand what are the cation properties, what are the nutrient reserves, what are the elemental balances, and various types of reactions which allowed or permitted in terms of understanding this soil chemical health. The third one is the biological health, which is more important relatively, as we understand the soil biodiversity, particularly the microbial and other diversities such as earthworm and other creatures are concerned. The soil organic carbon pool, the SOC, this is very important, and particularly it has it has a lot of bearing with respect to the climate change. The microbial biomass that also often determines or serves as an indicator as far as the health is concerned, the biological health is concerned, and the other pests and pathogens. So now I'll read out the biennial systems, particularly the biophysical, the physiochemical, the biochemical. So in terms of the biophysical, we have the bioprocesses, the bioturburation, the gaseous composition and fluxes, the methanogenesis, the nitrogenous and the denitrification properties. Coming to physiochemical, we have the thermodynamical properties, and that also includes the heat content and entropy. And then we have the redox potential, the charge properties that are combinedly put under the physiochemical categorization. Let us move on to biochemical. Under the biochemical, we have the soil organic matter, SOC, composition, and the biochemical transformation, the buffering capacity, the decomposition constant, and the anaerobiasis. So these all components, they together make or indicates about the soil health as far as the physical, chemical, and biological health is concerned. So now let us move on to the next slide that talks about the measurements. So measuring the physical, chemical, and biological attributes helps us in understanding various functions as far as the soil is concerned. So how we assess them? We assess them using various steps. The assessment steps to check soil health using indicators are the select indicators. So choose key soil properties such as pH, the soil organic matter, the microbes, and then you can build a minimum database. So how to build a minimum database? We need to pick the major or you say broader dominant indicators that helps us in easy monitoring. So important properties that the data set should help us in monitoring easily. So it can be possible if we are picking the easily measuring or the minimum parameters that serves as the broad indicators. Create interpretation indices. So make a scoring system to rate the soil health. This is how we usually go. We make a scoring system using SATI or some 1 to 10 or 0 to 1 kind of range, and then we go with respect to measuring or making the scoring system to rate the soil health. Finally, validation. Validation on farm. Test the system in real fields to see if it works. So how we need to do it? We need to test the system in real field. So some amount of field-based or ground-based studies which helps us in validation as far as what we have interpreted and what kind of indices we have taken in terms of scoring, in terms of score-based system. So it needs to be validated also on ground. So the ground also validation needs a sampling based protocol so that you address or you take care of as much as heterogeneity as possible as far as the validation system is concerned. Now let us move on to these broad properties which we can take or we can select as far as a minimum data set building is concerned. So one is the compaction. So bulk density which reflects the compaction. We can pick porosity because that maintains the soil structure and also affected by rain, which is easily monitored or can be monitored. Then we can also pick the infiltration. So that talks about the water absorption rate in soil as well as the rooting depth, which indicates the subsoil constants. As far as the chemical behavior is concerned, we can pick the few of these reserves as far as nutrients are concerned. So we all know about NPK. So if we pick few of them, then we can also try to relate them with respect to the measurement as far as productivity is concerned. So the gross productivity, the gross primary productivity or GPP. So pH, which tracks the acidification, also gets influenced by the soil organic matter. Salinity, that means the soil, the salt content, and it is also sensitive to rain. And now let us move on to the third one, the biological. If we have more of the soil organic matter, that indicates that the biodiversity level, and the soil organic carbon, which also it goes on decreasing with respect to the warming. So we'll discuss more about this in terms of the impacts as far as the warming or rise in temperature is concerned on soil organic carbon. Then the microbial biomass, yes, it helps us in terms of recycling the nutrients, thereby it contributes to a kind of more means what you say, maintaining the nutrient level on the upper soil. So, but the limitations, if we talk about, it rarely link soil health directly to climate change. So, we have to have some indirect protocols or things, indicators that can be linked to the climate change. So, soil health linkage as far as climate change is concerned. So, let us move on to the response. This particular diagram here talks about the relationship between soil structure and the climate change. So, on the upper side, if we take these are the major indicators as far as the carbon dioxide, one of the dominant greenhouse gases, precipitation, temperature, the intensity and frequency of storms and the droughts, particularly these kind of extreme weather events, and the sea level rises. So, if you take them and see their direct and indirect effects as far as the connectivity are concerned. So, as far as the direct effects are concerned, then the process of soil formation and degradation in terms of two components, biotic and abiotic. In abiotic, the wetting and drying property of the soil will be influenced by the process of soil formation or degradation. And then the freezing and thawing, the mechanic disturbances, rainfall impact and contribution. Coming to the biotic, we have the microbial, earthworm and also the termites. So, they also will be influenced with respect to this climate change, as we mentioned a few of the variables as far as the example is concerned. And then we will have indirect impacts on yield, particularly the yield in terms of productivity, and this direct effect also will lead to variation or alteration in soil structure, in turn leading to affecting the functioning and thereby also the yield as far as the productivity is concerned. So, this yield again will affect the quantity and quality of litter return. So, litter return means we will have the abiotic supplement going back to the soil. So, that will again affect the soil organic carbon and many more things, including the microbial reserve or microbial behavior of the soil. So, this is a kind of loop. So, frequent wet dry circles, weekends and aggregates, and intense rainfall cause erosion, drought a kind of compact risk, compaction of risk, and wildfire and deforestation. So, it exposes and the forest to a bare kind of situation, bare soil kind of situation, and leading to a soil, unstable soil. So, with respect to this understanding of relationship between soil structure and climate change, what are the adaptation mechanisms? So, adaptation is the future farming. So, in future we need to come out with a situation that need to adapt to relatively hotter and drier climates. So, that means what? The plant system has to adapt to relatively hotter or warmer temperature and little lesser what you say water moisture conditions, or even to say the drier climates. So, this also needs to be understood with respect to water use efficiency WUE via better infiltration and the storage behavior. The conservation tillage boosts soil stability, water infiltration and crop yield. So, one other solution to this is you do the tillage in terms of in terms of a very in a very conservation way. What do you mean by conservation way? You don't till the whole of the soil. You till the soil where you need to put the plant, or after putting the plant, when it germinates, you cover the rest of the soil so as to retain the moisture, so as to retain all other critical parameters as far as the soil is concerned. Many of these advanced countries, they have started adopting this, practicing this in terms of covering the upper soil by some polythene coated sheets. So this helps in terms of retaining the water or moisture level, in terms of water infiltration, and thereby boosts the crop yield. So this is the relationship between soil structure and climate change, has been published by Singh et al. Long back in 2011. And as far as the soil pH is concerned, it measures the acidity or alkalinity. So as all of us know, pH affects the nutrient availability and the microbial activity. So soil pH optimal is between 6 to 7.5, depending on what kind of area, means where it is, and what kind of supply it is accepting or it is having. So optimal is between 6 to 7.5. Acidic soil limit nutrients, and thereby a lot of toxin level increase. Alkaline soil, such as content of iron, zinc, and phosphorus in terms of higher proportions, and dominant proportion. And the linkage or the impact of climate change, if we have more and more rainfall, there will be more leaching, and the acidity will increase because the alkalinity behavior will decrease because of the leaching property of the upper soil. Then coming to the less rainfall, salt buildup make alkaline, and higher CO2 concentration, the organic matter will relatively decay at a higher rate, and higher temperature leads to higher microbial activity and organic material breakdown. So what we mean here, the alteration of the pH in terms of acidic and alkaline property will have repercussion on the soil pH health. And then in terms of climate change, simply taking the rainfall more or less, and high temperature as we are moving towards a warming world very fast, and the greenhouse gas concentration in terms of the higher concentration of the dominant greenhouse gases, that is carbon dioxide. So these all are going to affect the soil health. So in terms of the pH, and what are the management solutions? You can see on the left hand side the soil type and their pH range has been put there. This has been taken from a very old citation by Pittinger pair, and that itself says the variation of the soil pH from 4 to 10, and on the 4 side it is highly acidic and the 10 side it is highly alkaline. But as we mentioned in the beginning, the optimal is between 6 to 7.5. So what are the management and adaptation solutions we have? Add calcium carbonate or magnesium carbonate to convert acidic soil to a relatively neutral, close to 7 pH. Organic amendment also stabilizes the soil pH level in terms of additional alkalinity. Now let us move on to understanding the soil organic carbon balance. So carbon, that means we are talking about biomass. 50% of the biomass is carbon as a thumb rule. So the carbon in minus carbon out. So this is what is affected by several factors with respect to the soil organic carbon and soil health. So temperature, precipitation and water availability, elevated carbon dioxide, atmospheric nitrogen deposition, and fire. So let us look at the points under temperature. The decay rate doubles for every 10 degrees centigrade rise. The higher activation energy, more temperature sensitivity. Precipitation and water availability low, that means if it is less than 50%, it limits microbial activity. So there will be the decay rate will go down. in terms of optimal precipitation and water availability 50 to 70%, you will have rapid decay, and high, that means more than 80%, the oxygen shortage and decay in terms of soil organic carbon. Elevated carbon dioxide experiments have shown us that 1750 to 2009, we have a rise in carbon dioxide from 280 to 387 ppm. So, in terms of the loading of soil organic carbon, the C3 plants, the C3 group of plants have shown higher photosynthesis. Those are having nitrogen rich soil. It's not valid for others, because if you have more nutrients and dominantly nitrogen rich soil, they have shown higher means what you say, relatively directly proportional response to the elevated rise in carbon dioxide concentration. Whereas the C4 plants have shown relatively little response to the elevated CO2. And atmospheric nitrogen deposition in terms of 1 to 20 kg nitrogen per hectare per year, and the plant growth and soil plant growth will rise, and the soil organic sequestration also will increase. As far as the fire is concerned, yes, if more wildfire is there, then it will affect the top 2 to 3 centimeter of the soil. It will affect how? The ashes which are burned will lie there on the fire, on that top soil, and then if you are having the rain or precipitation, then it will be leached away. So that is how we have to understand that if it remains deposited there, then it will contribute to the recharging of the soil in terms of nutrients, in terms of carbon, or whatever way is possible. But then if you have the precipitation or rainfall, then it will leach away, leading to a relatively loss to the recharging property of the upper soil. Now, what are the management practices? We cannot have no till, we have to have minimum till, and pasture and agroforestry and crop choice helps to maintain the soil organic carbon. So we have to be very careful that we can, if as much as possible, we will avoid tilling of the soil, because once you expose the upper soil, it allows the carbon which is there in the upper soil to wash away by force of wind and the water in terms of erosion. And so if we leave it in terms of a pasture land or agroforestry, or if you go for a decisive choice of the crops, okay, so that will help maintain the soil organic carbon. Look at this these two diagrams on the right hand side, upper and lower. On the y-axis it is showing relative rate of decomposition, and on the x-axis for the upper one it is showing the temperature from 0 to 30 degree, and for the lower one it is showing the moisture, the soil moisture content in terms of percentage of saturation from 0 to 100, and both of them are showing a different indication. So as far as the operant response to temperature, it goes on increasing till attaining of 30 degrees centigrade. As far as the percent of saturation of soil moisture is there, beyond 60, it starts again, the saturation is at 60% level. So beyond that, it again starts declining. So this is how we can consider the availability of precipitation and temperature as far as the response to the soil decomposition is concerned. All of us also have studied about the nitrogen cycle. Nitrogen is the dominant gas also present in the atmosphere, but here we are talking about the soil nitrogen. This is one of the dominant nutrients. So nitrogen in soil and plants, key for chlorophyll. As all of us know, the nitrogen is one of the elements that is present in the chlorophyll pigment also, when we look at the structure of the chlorophyll. So chlorophyll, it also key component of proteins and enzymes. So understanding the nitrogen cycle is important, and it transforms via mineralization, nitrification, denitrification and fixation. But let us understand how it affects affected by the climate change. So climate change effects are, if there will be warming, there will be higher nitrification, and carbon dioxide alters the nitrogen uptake and balance. But coming to the management, organic and legume, they boost the nitrogen cycle. All of us know about the rotation between the kharif and the rabi crops. So the rabi crops, they have a kind of nodules in their the legume crops, they have a kind of nodule in their root system. So there you have a lot of nitrogen deposition. So when you go for a crop rotation, the nodules which is deposited on the roots, they are again retained by the same soil and used by the next crop, which is kharif. So in terms of crop rotation, this nitrogen is also very well getting complemented by both the crops. So time and place fertilizers well, and the proper irrigation and maintenance of the soil organic carbon is the key as far as the management is concerned in this warming world. And then coming to the measures soil respiration, we have both in terms of autotrophic and heterotrophic respiration. So root respiration and microbial respiration. The climate impacts, warming will lead to higher microbial activities, in turn lead to more of the CO2 escape or the carbon escape from the soil. Waterlogging and drought scenario will lead to relatively decrease in the respiration. Wet and dry cycles will lead to CO2 emission or burst, and high soil carbon dioxide will lead to more root growth and in terms of short-term carbon dioxide. And land use in terms of tillage and deforestation will lead to CO2 loss. So feedback and mechanism, management mechanisms could be, if warming and CO2 loop will have a positive feedback, cold soil permafrost pit will remain at risk. So what could be the mitigation solution? No-till and cover the crop as much as possible and go for afforestation, then so that moisture level will be conserved. That will also lead to stabilization of the soil respiration activities. Coming to soil biota, this is extremely important as far as the soil health and ecosystem function is concerned. It drives the decomposition and nutrient cycle, and the root microbe ties will lead to better root microbe ties will lead to better growth of the plants. The erosion and pollution will damage the biota or biotic system. So good microbial diversity leads to good soil or rich soil health. The soil biota sustains all the life. Look at the diagram that talks about the relation, the respiration, denitrification, the processes, photosynthesis, and the methanotrophy, the nitrogen fixation, the linkage with respect to various greenhouse gases as given by Singh et al. In 2011. So the traditional ways. What are the traditional or widely practiced ways of managing land for agriculture, forestry, and or the grazing? So one is, we can address the tillage and the stubbles. We can address the pastoral intensification. We can address the rangelands and the climate. We can also address the forest soil health and mine site rehabilitations. So if we manage the tillage and stubble, then we can protect the soil under various climate stress scenario. If we manage the pastoral intensification, then it will lead to, in terms of mitigation as far as rotational grazing and precision fertilizer is concerned. In terms of rangeland climate, the adaptation in terms of adaptation by selecting the native vegetation and the grazing management. The forest soil health, this for the forest can shift from carbon sink to source in terms of disturbance and many other fire and many other events, but the management, the various management solutions to protect the forest are afforestation, reforestation, selective logging, the controlled burning, soil conservation, pest pathogen management, and enrichment of the plantations. Coming to the mine site rehabilitation, yes, the adaptation could help in terms of soil monitoring and integrating the pest and avoid various compactions. The two interlinked wave diagrams, they have talks about the interrelationship and feedbacks among climate change, biodiversity loss, and the soil health. Is given again by Singh et al. In 2011. So, a forest-based bioenergy system. This forest-based biosystem, we can discuss it under three components: the organic farming, the biochar, the bioenergy system. They all help or lead to a climate smart soil management as far as the forest system is concerned. Finally, we have taken these three references to discuss about this particular topic on soil health and climate change. So, let us conclude with these 4 points. So, soil health depends on physical, chemical, and biological components supporting nutrient cycling and water retention. Climate change alters soil structure, pH, and organic matter through erosion, drought, and temperature rise. Improper conventional land use, that is intensive tillage, can degrade soil, reduce biodiversity, and deplete carbon storage. Climate smart soil management in terms of organic farming, biochar, bioenergy system enhances the soil organic carbon, fertility, and climate resilience. Thank you very much, friends, to join with me in terms of our discussion today on soil health and climate change. Thank you very much.